All right, we're picking back up. We're on question D in section 15.6. The problem asks us to compare the values of Q to K. And what does this tell us about anything? So we've got three possibilities. If Q is equal to K, that means that the reaction is in fact at equilibrium, because when we do the calculations, they are the same. If Q is greater than K, that means the reaction has gone too far and the reaction will shift back to the left. And of course, if Q is less than K, then the reaction hasn't yet gone to equilibrium and the reaction will shift to the right. Question E says to calculate QP for each of the given conditions and then determine in which direction the reaction is going to go in order to get to equilibrium. And they give us a table with some numerical values. So we know we've got our Kp expression, SO2 squared times O2 divided by SO3 squared. And all we do is fill in the numbers and see where are we right now. Well, when we do the first situation, Qp is 4. And so the equilibrium will shift back to the left because Kp is only 0.338 at this temperature. In the second scenario, when we calculate it, Qp is 0.125, so it's less than Kp, so we would shift the equilibrium back to the right. And then, of course, in the third scenario, Qp is in fact equal to 0.338, which means that it's equal to Kp. So we are at equilibrium. All right, now we move on to question F. We've got a new reaction. We've got hydrogen plus iodine reacts to form 2 moles of hydrogen iodide. Kc is 50.5 at this temperature. So we want to answer the following questions regarding the equilibrium system represented by this equation. So we've got our values there, and we need to calculate the concentration of hydrogen iodide in this mixture. All right, so we write our equilibrium expression. We say that Kc is equal to Hi squared divided by the product of the pressure of H times the pressure of I, the concentrations of these. And so we crunch in, we put in the numbers and just crunch the math and see what we get. And we get Hi is equal to 3.30 molar. And we can use this expression because the problem tells us we are at equilibrium. All right, part 2 says hydrogen gas and iodine vapor were added to a previously evacuated flask, and the initial concentration was equal to 2.00 molar. And now the system goes to equilibrium, and we want to calculate the concentration of all 3 species at this new position. All right, so we set up our rice box. We write our reaction equation. We write our initial concentration of 2, 2, and 0. We know that from stoichiometry, we're going to lose some amount of hydrogen and iodine. That would be X, and stoichiometry tells us we will gain 2x of Hi. So our equilibrium conditions are now 2 minus x, 2 minus x, and 2x. So when we fill all this into our equilibrium expression, we can get, we fill all of this in and we get that the value of Hi, it turns out to be 3.12 molar. Because when we solve for Hi, it's equal to I. I solve for H, it's equal to I, and it becomes 0.44. So our equilibrium concentration would be 2 minus that, or 3.12 molar. All right, part 3 says hydrogen gas and iodine vapor were added to a previously evacuated flask. The initial concentration of Hi was equal to 2. This is a little bit different than the previous problem. Here, Hi is equal to 2, and now we allow ourselves to reach equilibrium and we calculate the concentration. All right, so again, we set up our rice box. We have our reaction equation. We have our initial concentrations, which now are 0 and 0 for hydrogen and iodine, but 2 molar for HI. We do our change concentrations. We can see that if all we have is HI, the reaction is definitely going to move to the left. So we are going to form some hydrogen and some iodine. So X and minus 2X from stoichiometry. So our equilibrium conditions will be 0 plus X, 0 plus X, and 2 minus 2X. All right, we write our equilibrium expression, and we plug in all of the things that we know, and we solve for X. And here, when we solve for X, we get 0.22. So that must mean that the concentration of hydrogen gas and iodine vapor is 0.22, and the concentration of hydrogen iodine at equilibrium will be 2 minus 2 times 0.22, or 1.56 molar. Part 4. All 3 gases added to a previously evacuated flask. The initial concentration of each one of them is now equal to 2, and we need to compute what the concentration is of all 3 species at equilibrium. Well, we know how this is going to go. We can compute Q, and when we do, we see that Q is equal to 1. Well, Q is less than K because K is 50.5. So the reaction is going to move to the right because Q is less than K. All right, now we set up our rice box. We write in our reaction equation. We write in our initial concentrations. Everybody is at 2 molar. We write in our changes due to stoichiometry, and we compute what our equilibrium positions are going to be. And we plug in those equilibrium positions into our expression for Kc. And when we solve for X, we get 1.34. So that must mean that hydrogen and iodine would be 2 minus 1.34, or 0.66, and hydrogen iodide will be 2 plus 2 times 1.34, or 4.68. You should be confirming my math in all of these because we'll be doing a number of these problems as we go through the unit. All right, section 15.7, Le Chatelier's principle. So the diagram at right represents the percent yield obtained from the synthesis of ammonia, where we've got hydrogen and nitrogen combined in a 3-to-1 molar ratio at various temperatures and pressures. And you can look at this diagram, which has been made for us by the author of the book. We see at question 1, as the pressures increase from 200 to 500 atmospheres, the percent yield increases. It goes up, and we can just look at that along the axis on the left-hand side. Now, when we look at the temperature, the axis on the right-hand side, as the temperature goes up from 400 to 550, the percent yield goes down. So as you can tell from part A, an equilibrium system can be affected by various changes in pressure or temperature. And these changes in concentration can also affect the equilibrium. And we want to define Le Chatelier's principle. This is on page 633 of our book. So if you have your book, you definitely want to find this in your book. And Le Chatelier's principle says this: if a system at equilibrium is disturbed by a change in pressure, temperature, or concentration, the system will shift its equilibrium position to counter this disturbance. It always wants to get back to equilibrium. So let's talk through a couple of problems here. Section 15.4. Well, it's not 15.4, it continues to be 15.7. We've got A plus B reacts to form C, And question C says, suppose we have an equilibrium at 500 K between substances A, B, and C as shown. At equilibrium, A is 1 molar, B is 2 molar, and C is 5 molar. What is the value of Kc for this reaction at 500 K? Well, we can write our equilibrium expression. We know it's equal to the products raised to their stoichiometric coefficients divided by the reactants raised to their stoichiometric coefficients. In our case, they're all 1, so I would have 5 divided by 1 times 2, or 2.5. Now the problem says that additional B was injected into the equilibrium mixture at 500 until the concentration of B becomes 4 molar. The following rice box has been created based on this change. All right, so we've got our initial concentration now of 1 and 4 and 5. So we look at our change. According to the stoichiometry, A will be minus X, B will be minus X, and C will be plus X. And we want to compare QC to Kc and decide if the equilibrium should shift to the left or toward the right as a result of this change. When we look at our equilibrium positions, we're now going to be 1 minus X, 4 minus X, and 5 plus X. So Q will now be 5 divided by 4 times 1, or 1.25. Q is less than K, so the equilibrium shifts to the right. All right, now the next question says we want to use the rice box and some algebra, which unfortunately is going to include the quadratic for this problem, to calculate the new concentrations of A, B, and C after we get back to equilibrium. So we plug in our change, minus X, and plus X. We write down our equilibrium positions. Now we look at our K computation. Well, we have K is equal to 5 plus X divided by 1 minus X times 4 minus X, and that's equal to 2.5. Now when I grind through this, I actually do have a quadratic that I've got to solve. My quadratic is 0 equals 2.5x squared minus 13.5x plus 5. You should do all of this math and make sure that you are comfortable with getting to this point and developing your own quadratic. And you should also have a quadratic solver in your calculator. You can do it online, but you won't be able to do it online in the exam. Now, when we plug all this in, we get X is equal to 0.4 and X is equal to 5. But we can rule out X is equal to 5 because if we were to use that value, we won't get anything that makes any sense because we would get to negative concentrations. So although that's a solution algebraically, it's not a solution chemically. So we stay with X is equal to 0.4 and we fill in the bottom row of our table. 1 minus 0.4 is 0.6, 4 minus 0.4 is 3.6, and 5 plus 0.4 is 5.4. So now we can fill in the bottom row of the table. What is our equilibrium concentration? And that gives us our final answer to this problem. All right. This is a good point to stop, so we'll pick this up in the next video. This series of videos, this lesson is a bit more complex than previous ones, so it's taking a bit longer to discuss all of the notes.